Okay, hey everyone. Thanks for bearing with me. Welcome. This is a joint work between myself and Shalev Ben David, and it is concerning the age-old question of if you have a random algorithm that is wrong some of the time, how much does it cost to upgrade to an algorithm which is wrong none of the time? And we come up with a sort of equivalency here in the query complexity world. Now, for those of you not aware, query complexity is when you're given a Boolean function and the task is to compute the Boolean function with the fewest amount of query to the input bits as possible. So the input comes in hidden, and we don't care about time or space. We're just minimizing the queries to the input bits. So we're going to talk about the query complexity analogs of BPP, bounded error random algorithms, and ZPP, zero error random algorithms. And the reason why query complexity is interesting is because you can come up with a lot of elegant separations that are still open in the classical world, as we're going to see. So the object of interest is composed functions. If you have a Boolean function f on n input bits and another Boolean function g, then f of g is when you take n copies of g and each one has its own fresh set of inputs. Those outputs go back up to f, and you have f of g. And in specific, we're interested in self-composition. So f of f k times, we call this f to the k. And so as you can see here in the tree, f would have n children, which are copies of itself, and all the way down to the leaves where you have n to the k input bits. That is the input for f. And the reason why we care about this construction is that these are sort of the workhorse of query complexity. This is how we show a lot of the relations and separations between different query complexity measures. So take any query measure, call it m. The cost of m of f to the k usually grows something like c to the k. And that base c is what's interesting to us because it describes, like at each level of recursion, how much is the blowup, right? And we can define this formally with m star, which we call the composition limit. M star of f is the limit as k goes to infinity of m of f to the k to the 1 over k. And this 1 over k sort of normalizes this exponential blowup and lets us take out the base of the exponent. Now, there are two famous measures in query complexity that we already understand this composition limit for. D star of f, which is the deterministic query complexity, is equal to d of f. In general, in query complexity, you study deterministic, randomized, and quantum query complexity. And that's part of the reason why quantum theorists like query complexity is that it shows quantum advantage in very elegant ways. For quantum, Q star of f is known to be the negative weight adversary bound. Much less understood is randomized query complexity. And that's where our results really lie. In fact, it is so poorly understood that it is not even known whether or not R star of f is computable as a function of f's truth table. Like, you give me a function f, I cannot even in principle tell you perhaps its value R star of f. Now, we've pinned it down on two notable functions. Sachs and Wigderson pinned it down on the NAND tree, and you get this value, which is about 1.686 for R star of NAND. And the 3 majority function, very famous, we've not been able to compute it, but we've been able to pin down a range for it. And I just want to really stress, like, even for an 8-bit truth table, we're not able to compute R star of f here. Now, our result concerns this key distinction between these two notions of randomness. The bounded error notion, where an algorithm can be wrong less than 1/2 of the time. As long as it's less than 1/2, we can always amplify down the error. And the Las Vegas notion, where the algorithm is always correct, but we measure its cost in the expected case. Now, classically, Monte Carlo is at most Las Vegas, is at most deterministic, but what about the other way around? Like, what is exactly the separation between Monte Carlo and Las Vegas in the query complexity world? In the NAND tree case, they did coincide. R0 star and R star were the same. This led people to speculate that R0 and R are just the same up to constant factors. This was not true, and Binus and co-authors proved there is a polynomial separation between R0 and R. In fact, if you allow partial functions, partial Boolean functions are functions that do not have to have the whole set of n-bit Boolean strings as their domain, like they can be promised to have an input of a specific type. You can even have an exponential separation between partial Boolean functions on these two measures, R and R0. The question is, what happens in the composition limit? And that's where things get interesting, and that's where our result is. For any possibly partial Boolean function, R0 star of f is equal to the max of R star of f and C star of f. Now, C is the certificate complexity of a Boolean function. Remember, in query complexity, we are querying the input bits to discover the output of the Boolean function. The certificate is the minimum number of bits that you need to uncover to prove that the function has a specific output. So it is, and those bits that you uncover to do that, they compose the certificate. So essentially what we're saying is that as long as certificate complexity is not the bottleneck, in the limit, Monte Carlo upgrades to Las Vegas for free, which is pretty interesting. Two quick consequences of this. Going back to 3 majority, R0 star of 3 majority is R star of 3 majority. And these two quantities were studied separately, and now we know them to be equal. We don't know what the value is, but we have equated these two unknowns. In the quantum world, quick side note, quantum algorithms in query complexity don't have to produce a certificate. But if we force it to produce a certificate, we get a quantum analog. And QC is quantum, which is forced to produce a certificate. QC star of f is equal to the max of Q star and C star. And the proof skeleton is the same. So what is the proof? It's an equality. So lower bound direction is pretty easy because R0 is just plainly larger than R, and R0 is 0 error, so it has to produce a certificate, so R0 is greater than certificate complexity as well. The interesting part is going to be in the upper bound direction. So in the upper bound direction, we have to design a Las Vegas algorithm for f to the k. And we're going to do that recursively. We're going to assume we can do it for f to the k minus 1. And now we have to build a certificate finder for f to the k. We call that a sub k. So the first step is that we're going to take the children of f and we're going to run a Monte Carlo algorithm on each one to come up with an estimate. And we're going to run it multiple times to amplify the error down to less than or equal to 1 over 4n. This is like, we know with very high probability what each of these children are, but we can't know for sure. But this gives us a union bound that this provisional estimate of the values for f's children is at least 3/4. From these provisional values, we are going to pick the cheapest certificate, and we're going to recurse down into this, each one of these children that are constituent parts of this certificate in order to verify that our guess was correct. So when we do the recursive step, there are two possibilities. Either our guess was correct and the recursive step found the certificate, which is great. We merge that into the rest of the outputs and get a certificate for f. The other case is that a sub k minus 1, the recursive step, returns a null character, and either that's because our guess was wrong and so finding a certificate is impossible, that doesn't find one, or it's still possible that if the guess was correct, that a sub k minus 1 fails to find a certificate. So essentially, in this algorithm, we are balancing between these amplification steps, both at the level of running these Monte Carlo algorithms and at the level of running these a sub k minus 1s. And we want to get to a place where we can sort of zero all this out with composition limits. So let's count the queries here. Let q sub k here be the total number of queries made by this certificate algorithm. You have two terms here. You have a polylog times r of f to the k minus 1. This was the cost of our Monte Carlo runs to find the estimates. And you have a polylog in c of f because remember that the amount of times we had to run that recursive step, the number of children we had to do it for, is at most C of f number of children times qk minus 1, which is our recursive call. When we unroll that geometric recursion taking the expected cost, we get an R0 of f to the k is a n up to logs times R of f plus C of f to the k. Now remember our definition for the composition limit. We take the kth root of both sides, and we take the limit as k to infinity, and we get that R0 star of f is at most up to logs R of f plus C of f. But this is still far away from what we need because R of f and C of f can in general dwarf R star and C star. So there's a trick we do. We take the star of both sides. Our paper, we prove some properties about the star operator, which helps, simplify this proof. Idempotence, starring a star doesn't do anything. It turns sums into maxes, and it eliminates constants and log factors. So when you do that and you star both sides of this inequality, you get the desired upper bound that we were looking for, and all of these ugly, factors wash out. And so that's really the nice part, is that, there was this like very crude amplifications being done, repetitions being done, and the star operator made it very generous for us to be able to kind of get back out to a clean result. Now, one last, red hair, or like one last side note here is like, does this limit even exist? We assume this composition limit existed in the presentation. In the paper, we do prove it. You might be tempted to use Fichetti on log of m of f to the k to try to prove that this composition limit exists, but the measures are only nearly submultiplicative. So to fix that, instead of looking at all of k, you look at a divisibility chain. K1 divides K2 divides K3 and so on. And along a chain like that, the near multiplicative error telescopes cleanly. So you arrange the odd steps to approach the lim sup and the even steps to approach the lim inf, and the divisibility lets you squeeze them together. And this works pretty much for any reasonable measure: deterministic, randomized, Las Vegas, quantum, certificate complexity, or degree, etc. So what that leaves us with is that is R star of f still computable? We don't know, but answering that would also settle R0 star of f. What is R star of 3 majority? That's still stuck. We don't know the actual answer to that, but we do know that it's R0 star. And does the certificate finding strategy extend to other measures like approximate degree? That's something that can also be explored in further work. So that concludes the talk. Just to reiterate, we can go from Monte Carlo to Las Vegas in the composition limit within the query complexity world pretty much for free, except in this with this certificate complexity caveat. Thanks for listening. And thanks for letting me use your laptop.
Sure. We have time for questions. So, what are the examples where there's a big discrepancy between these R star and C star?
Between like examples in R and
Yes,
R.
C star is much larger than R star.
C star is much larger than R star. In promise or, you have a part. This is really only for certain partial functions. So let's say you have a Boolean function which either at least 2/3 of the inputs bits are 1 or they're not. Then random sampling, you can easily find the answer with bounded error, but actually identifying a full certificate for the majority is going to be hard. Yeah.
Okay, no further questions.
Thank you.
Okay.